Hi everyone. Today's video lesson is going to be starting off with the problem of calculus. This is a problem that Sir Isaac Newton and this guy named Gottfried Leibniz, they were all working on this problem several hundred years ago. And what they were interested in is how fast an object goes at any instant in time. Now, what this graph is doing is showing an example of some sort of displacement function, like an object is moving through space away from its starting point and then back again towards its starting point. And suppose we were interested in exactly how fast that object is going at any moment in time. Well, we did not have necessarily the tools for that, but we did have tools for finding an average rate of change over any time period. So here, for example, you can see that the object is increasing its distance, but that increase is slowing down. It's increasing by less and less and less, and at this point the object actually stops and turns around and starts going in the other direction. However, when I find the average rate of change, what I'm doing is taking all those variable speeds and smoothing it out into one straight line. And that line, if we find its slope, will represent the average speed that the object traveled over that time. But since the object was traveling faster here and is traveling in the opposite direction here, this average rate is inadequate for determining the speed of the object at this one specific time. So naturally, we would be interested in moving closer to get a better estimate. Oops. So this moves my point much, much closer, and it gives me an approximation for the speed at this one specific point. It's going to be somewhere around 2.9. So maybe it'll be around 3. Let's see if it gets even closer. Yep, as I get closer, this number gets closer and closer to being 3. The problem is, if we wanted to know the exact value, we move this point so that it's right on top. All of a sudden, my tangent line disappears, and the slope is undefined. Now, if I move just a smidge away, there is a tangent line, and the slope is very close to being 3. But when I get to the exact spot, the slope becomes undefined, and we're unable to find the exact value of the speed at that point. Now, we can infer that it's probably 3, but how do we mathematically prove that? And that is the problem of calculus. Now, before we actually get into the calculus, we want to learn how to set up an average rate of change in a way that is going to make our calculations easier to deal with. This is the way we typically calculate rate of change. We take the difference in the y's and the difference in the x's and we put them into a ratio. But we can see on this graph, we are going to define a starting value at a, and then we are going to go h units away to create an interval. And to get the y values, we have the value a, which is here. My graph is a little transposed. Let me do something here. Switch this back around. There, now it's going to be more consistent. I have this a value here, and here I have this other value that's a plus h. In other words, this value is h units farther away from a. To get the y values, then, I just put a into the function. So to get the y value for a, I just put f of a, and for a plus h, it gives me the y value f of a plus h. And then to get the change in y, I subtract f of a plus h, gives me this whole line, and then I subtract f of a, which is this guy down here, and that leaves me with the difference, which is the change in y. So that's why I have this ratio that shows f of a plus h minus f of a to represent the change in y, and then I have the number h to represent the change in x. So the rest of this lesson is focused on just the mechanics of using this alternative form of an average rate of change ratio. So we understand that conceptually why. What we're trying to do is to see if we can figure out the problem of what happens at instantaneous velocity. What happens when h equals 0 and we end up with an undefined ratio? How can we get around that fact is the basic premise here. So here we get into the mechanics then. Suppose I had a function f of x equals negative x squared plus 4x, and I wanted to know exactly how fast that object, if this represents a displacement of an object, exactly how fast is that object moving at time 2. Well, I'm going to start by representing the function as a graph. I'm going to find out where x equals 2, And then what I'm going to do is establish some arbitrary number h. It could be anywhere to the right or left, it doesn't matter, but we like to put h to the right so that we can consider h a positive number. It's just easier to think that way. So I just pick an arbitrary point randomly on the graph, and then the distance along the x-axis between those 2 points is what we're going to define to be h. So on the x-axis then we have 2, and then we can follow it up to the function to find out what f of 2 is. And here we're going to have h plus 2, and we can follow that up to the function to find f of 2 plus h, or h plus 2. So here are the 2 points. And to calculate the change in y over change in x, I'm going to subtract the y values, f of 2 plus h minus f of 2, and then I'm going to take the h as the change in x, because h is literally the change in x. So now I just have to take my function and evaluate f of 2 plus h. So I could do that down here. There's f of 2, and here's f of 2 plus h. So I can write f of 2 plus h here, and then subtract f of 2. I know f of 2 is 4, and f of 2 plus h is this hot mess right here, this algebraic expression. But I can make this better just by doing a little bit of cosmetics. I'm going to first recognize that 2 plus h squared, hopefully we remember by now that that has to be FOILed. Multiply the 2 by the h, the 2 by the 2, the h by the 2, and the h by the h, and we end up with 4 plus 4h plus h squared. Now all that has to be made negative. Also here, I'm going to distribute the 4 into the 2 plus h. And don't forget to bring down the minus 4. And that's all going to be divided by h. Then I'm going to distribute the negative and collect like terms. And notice that here I have a minus 4 and a minus 4 and a plus 8. If I add all those together, I get 0. So basically they all add up to 0, which leaves me with 4h positive and a 4h negative. Well, those things subtract out too, so all I have is a negative h squared all over h. And if I take negative h squared divided by h, that's just negative h. Ooh, negative h. So apparently the slope of this line right here is now a function of the interval h that I chose. So for example, if I chose h to be 1, then the slope of my secant line is going to be negative 1. Which makes sense. You can see it going downhill. It's going to be a negative number. Now, I can verify this to be true by going back to my Desmos graph, just transposing all the stuff from the previous slide here. But if h is 2, then the slope of the the slope of the secant line should be negative 2. So we go to that Desmos file, and I'll even show you how to do this. Go back to the Desmos file, and I can change the function to be the function that we were working with. Just a quick peek. It was negative x squared plus 4x. So I type in negative x squared plus 4x. I wanted to find the slope at 2, so I'm going to put a to be 2, and then I'm going to make b any number so that h is 2, because you can see on my work, in order to check my answer, I'm like, well, let's take this slope of this secant line and let h equal 2, which means the slope of the secant line should be negative 2. So in my Desmos, I change the b value until it changes this h to be the number 2. So in other words, 4. Now h is 2, and look, the slope of the secant line is negative 2 when I start with x equals 2 up here and let h equal 2 here. It makes the slope be negative 2. So today's lesson was brought to you by the number 2. So this is a way that you can use Desmos to make sure that all of this algebra was done correctly. We have to consider ourselves error-prone human beings, and so it's likely we might drop a negative or do something screwy here. We will know if we did all this algebra right for a lot of reasons, but one of them is if we check on Desmos to make sure that we just choose a random value for h, that this formula produces the slope. And this will tell you what the slope is, this will tell you what h is, and this will tell you the point where you're starting, the starting point. So I want to make this video wrap up real quick, so I'm going to fly through this one. If you're in my class, you can get these notes. If you're out there in the ether, just do a screen capture to see. But the same principles hold. The first is to make a graph, and on that graph, try to represent the problem. So we're starting at x equals 7, and then we pick some arbitrary h units away, and that gives us 7 and f of 7, and it also gives us 7 plus h, comma, f of 7 plus h. So we can calculate f of 7 here, and we calculate f of 7 plus h here, and then all we have to do, we start by writing this formula always, f of 7 plus h minus f of 7 all over h. F of 7 plus h we said down here, and f of 7 we said is 1. And here's a trick for making your notation work for you. You'd have this nasty fraction, and I'd have to make all over h. That would be a really irritating flow. So I take the divided by h and express it as times 1 over h. So basically you can move the h as a little fraction off to the side instead of having to make these extra fraction-y fractions. Anyway, to simplify the denominator here, and to get a common denominator here, so that I can add these two numbers together. And when I do that, I end up with negative h over 2 plus h. I told you I was flying. You can freeze frame if you want to see exactly what's going on step by step. But then the h's divide out, and I end up with negative 1 over 2 plus h. So this formula, if I just choose whatever number I want for the interval h, this formula will give me the slope of this secant line. And to verify, I go back to Desmos and I change the function to 2 over x minus 5, which is my given function. I let x equal 7, so that's my a value. And then I set the b value so that, again, I just arbitrarily picked 2. I could have said 3, 4, 5. I could have said a half. It doesn't matter. I just chose a value for b that makes h equal 2 and use my formula. My formula says I should have a negative 1/4 slope, and sure enough, so too does Desmos tell me I should have a negative 1/4 slope. So that's how you find slope using pre-calculus techniques and how you check your answers. So hopefully this was helpful, and thanks for watching.